Let's take a very difficult problem, apparently difficult, okay. How many members there are? 7 members, but fortunately there is some symmetry in this structure. Can you tell me what is the minimum degree of kinematic indeterminacy in this structure? Okay, on top of that you have a concentrated moment acting at O and B, 45 kilonewtons. It's as messy as it can get. This is a very challenging problem. Okay, something we can ask in your GATE exam, but it takes you only 5 minutes to solve if you are smart and you know what's going on. So carefully you'll see, look at the way direction it's going to roll. It's going to roll this way. It cannot take a horizontal reaction this way. If it cannot take a horizontal reaction this way, this member DO is going to behave like a cantilever. Very important to understand. It's a cantilever. Remember we did the problem with an overhang? Similarly, you must treat this. This is already known. This OD is statically determinate. I know the bending moment diagram in OD in advance. So, really speaking, I have only one unknown. You see, the displacement method is so powerful here. And how do I solve for this unknown? So, I want you to do this. Let's do it together on the board. You have some load here. I'm not writing the values. You have UDL here. And you have a load here. And you have a moment acting here. By the way, this element we can separate out. That element is DO. This is O. A. This I presume is B. And this is C. This element OD has a concentrated load acting here, whose magnitude is 50 kilonewton, and this is 2 meters. So this part is already known. There's no reaction possible here, so you get a shear force here, 50 kilonewton, and you have got a moment here. 15 to 2 is 100 kilonewton. Now this effect will get transmitted here, right? And it's going to be a clockwise moment. So this 100 will come here, but there's already a 45 kilonewton meter acting there in the original problem. So you have a net moment here of 145 kilonewton. So this is the problem that you need to solve. So that huge problem has simplified to this problem, this part. How do you solve this problem? Well, first let's find the fixed end moments you need to find for this element, and for this element. Do that. I think I have the solutions here. That's the horizontal AO element. We have a constant load bang in the middle, so very easy to capture, get minus 3. So 3 will be WL squared by 4, and it's going, so it's going to be minus 45. I hope you remember all this. So these are the fixed end moments you get for AO and OC. For OB, it's going to be, it's hinged at B, so MF OB should be done carefully. MF not OB will be 1.5 times WL by 8. Okay, and be careful about the direction. Direction will be clockwise. I hope you get this. So W is 80, L is 3 meters, WL by 8, and that's it. Now let's try to do it together. So let me remove this part. Let's write the basic slope deflection equation. MAO, MOA, MOB, MOC, MCO. This is equal to MF naught AO, MF naught OA, sorry, MF naught OB. This is all MF OA, AO, and MF OA. This is going to be MF OC and MF CO, which we have already calculated, plus something which we'll write here into EI into theta naught. There's only one unknown. So as far as this element is concerned, remember what you will write mechanically. MA naught is MF A naught plus 4 EI by L into theta A, which is 0, plus 2 EI by L into theta naught. So you will write here 2 by 3. L is 3 for all the methods. Agreed? Now you take this element. So it will be 4 by 3. I hope all of you agree. 4 by 3. Next you take MF naught OB. What should it be? MOB, the far end is hinge. So it will be 3 EI by L. So it will be 3 by 3 or 1. And when this is guided fixed support, what should it be? MOC is MFOC plus EI by L, which will be 1 by 3. And the other one will be an incident kilonewton. So next step is we have to write down the equilibrium equation. What's equilibrium equation? Everything should add up here to plus 145 kilonewton. Do we have that here? Okay. So equilibrium equation is M corresponding to theta naught is M OA plus M plus 145 kilonewton. So let's do that. So you have to basically add these 3 quantities and these 3 quantities, correct? If you add them up, what do you get? You get minus 15 plus 8 by 3 EI theta naught is equal to plus 145. Very easy to solve. You get EI theta naught equal to 60 kilonewton. Well, you need not write the units. If you want, EI will always have units of kilonewton meter squared, and theta is in radians. So if you want, you can write, nothing wrong. So being correct, or you write units. You got this. It's plus. It has to be plus because you have a constant moment acting there. And now you plug in this value here, and you'll get the final answers. The final answers are plus 10, plus 110. That's it. Not difficult. Huh? Simple. 5 minutes. You can actually crack this problem. And after you do that, you can draw your bending moment diagram. Very simple. Any queries? This is a good problem to solve. Any queries? Of course, here I've drawn only one half. Symmetrically, you can draw the mirror image. I'll start you off on it, then we'll take a short break. But tell me, what is the degree of kinematic indeterminacy? Take advantage of the fact that you have a hinged end at D. You have fixity at A, E, and F. So this is a frame. Okay. The triangular load you could get due to hydrostatic pressure or soil pressure in the vertical element. So your only unknowns are theta B and theta C. You can ignore theta D. Okay, I'll just start off this problem. First, find the fixed end moments. The UDL is straightforward, but the triangular load you have to remember the formula or derive it. So the fixed end moments for AB are very simple, minus Q naught L squared by 12. For BC and CB is also simple, same by Q naught L squared by 12. L is 4 meters. For CD, you have to correctly write it as MF naught CD and take 1.5 times the fixed end moment. So minus 75. And for BE, the formula is minus Q naught L squared by 20, where the loading is maximum, and Q naught L squared by 30, where the loading is 0. So these are formulas you need to apply. We've got the fixed end moments. Now the next step is to write it neatly in a matrix form and write down next the slope deflection equation. For AB, it is MFAB plus 4EI by L into theta A. Theta A is 0. So you have to write only for theta B. It's 2EI by L for AB and 4EI by L for B. And you have to correctly write the EI value. Okay, otherwise you'll make a mistake. AB has an EI of 2 EI, and its L is 5 meters. Similarly, write for BC. Okay, in BC, both theta B and theta C will have a role. Both are unknown. And write for CD. For CD, you have to write MF naught CD plus 3 EI by L. EI is again 2 EI and L is 5 meters. Okay, so we've written the slope deflection equation for all the horizontal elements. Now you write for the vertical elements. For the element EB, MEB is MFEB plus 2 EI by L of theta B because theta E is 0. And for MBE, it's MFB plus 4 EI by L for theta B. L is 4 meters. Similarly, you write for FC. There is no fixed end moment for FC, so you can simplify that. So if you simplify these equations, they come to this point. And the whole thing you can write nicely in a matrix form like this. Make this a habit. You can even draw some horizontal lines the way I've done it to separate out your beam elements. So you got your stiffness measures, you got your fixed end moments, you have only two unknowns, theta B and theta C. How do you get them? You have to get the equilibrium equation. Now remember, there was a concentrated moment at one of those joints. If you go back to the original problem, there is a moment at C whose value is 40 kilonewton meter. So when you write the equilibrium equation at C, you must include this minus 40. How do we do that? Write the equilibrium equation. For theta B, add up all the moments, n moments collecting at B, put it equal to 0, MBA, MBC, MBE, there are 3 members. And for C, MCB, MCD, MCF, you should put equal to minus 40. Be careful. You've got two equations, solve them simultaneously, find out theta b and theta c, plug in those values, you got your answer. So even a problem apparently so complicated as this is actually very easy to solve. And once you have the free bodies, you can draw the free bodies. I won't get into this. You can do this problem. It's solved in the book also. And you can find your shear forces, etc., etc. Okay, so this can be done. I'm interested in the bending moment diagram. And this is what it will look like. Okay, we move on. You can draw the shear force diagram and actual force diagram also if you wish.